Hello everyone, welcome to this video lecture. I am Ramesh Kumar in Mathematics department. My topic is Real Analysis 1 in Countable set. In this video lecture, we are going to see about basic subset theory, basic concepts of functions, and countable set, uncountable sets, and theorems on countable set. First of all, set. What is set? The collection of well-defined objects is called set. Well-defined means we have to specify some extraordinary characters or behaviors like that. A height, the students are all are height, the short students like that. This is called set. Elements are members. The objects in the collection will be called elements or members of the set, and they will be said to belong to or to be contained in the set. Note, the set will be denoted by always capital letters A, B, C and elements by lowercase a, b, c. We write x belongs to S to mean that x is an element of the set S, and we write x does not belong to S means that x is not an element of the set. For example, the set of positive integers less than 10 is denoted by S equal to 2, 4, 6, 8. The set of all S equal to braces, open braces and curly braces, open braces 2, 4, 6, 8, then ending braces. The elements are separated by commas. Subset. A set P is said to be a subset of S whenever every element of P also belongs to S. Ordered pairs. A set of two elements A and B as being ordered. These all enclose the elements in parentheses A, B. Then A is called the first element and B is called the second element. The next Cartesian product. Cartesian invented the set. Given two sets capital A and capital B, the set of all ordered pairs A, B such that A belongs to capital A and small b belongs to capital B, then it's called the Cartesian product of A and B, and it is denoted by A cross B. Simply, the first element belongs to the first set and the second element belongs to the second set. The elements are in between parentheses, it's separated by commas. If capital R denote the set of all real numbers, then ordered pairs or Cartesian product R cross R is the set of all complex numbers. Next, relation. Any set of ordered pairs is called a relations. Suppose A to B means A related to B, C related to D, then C is relation of. Then function. A function f is a set of ordered pairs x, y, no two of which have the same first number. This is the definition for function. Next, restriction of f to functions f and g satisfy the inclusion relation G. Subs contained in f, we say that G is a restriction of f or that f is an extension of G. In particular, if S is a subset of D of A and F is G is defined by the equation G of x equal to f of x for any set S, then we call G is the restriction of f set S. Next, one-to-one function. The function f is defined on S, then the function f is said to be 1, 1 if and only if every x and y in S, f of capital F of x equal to f of y implies x equal to. Otherwise, we can say that x not equal to y, then the function f of x not equal to f of y. This is also same meaning. Or a function which is one assigns distinct function value to distinct members of S. There are three kinds of definitions. One function is also called injective function. Converse of a relation. Converse of a relation is denoted by S dash and defined by A, B is from B, A that belongs to S is called the converse of S. Then inverse of a function. The converse relation f dash is a function, then this is called inverse of a function. Suppose that the relation f is a function, consider converse relation f dash, which may or may not be a function. But if f dash is also a function, then f dash is called the inverse of the function. Inverse. This is the example of inverse function or converse relation. Next theorem. If the function f is 1, 1 on its domain, then prove that f dash is also a function. So given is f is 1, 1 function, then we got to prove f dash the inverse relations or converse inverse function or converse relation is also a function. Given that f is 1, 1 function, to prove f dash is a function, then we know that x, y belongs to f dash and x, z belongs to f dash, then y equal to z because it is a 1, 1 function. So according to the function of according to the 1, 1 definition, x, y belongs to f dash and x, z belongs to f dash, then y equal to z because that x is the same number and y equal to z is the different numbers. But given f dash is a converse function, therefore if x, y belongs to f dash, then compulsory y, x belongs to f dash. This is according to the definitions. that is x equal to f of y. It is taken as equation number 1. Next, x comma z belongs to, similarly we can define x comma z belongs to f dash, and that argument is going like that. That means that x equal to f of z. This is taken as second equation. Now comparing the equations 1 and 2, we get left hand side is equal to x. The both equations are get x. Then right hand side must be equal, that f of y equal to f of z. This implies that y equal to z because of one function. Hence f dash is a function. Next, composite function. Given two functions f and g such that if r of f subset of d of g, we can form a new function, composite function. It is denoted by g circle f, and it is defined as g composite f of x equal to g of f of x. Next, note, g composite f not equal to f composite g, because g composite is different values and f composite is different values. Therefore it is not true. That is, commutative is not true according to the composite function. Then associative law, chi composite g composite f, which is equal to chi composite g composite. Next, what is sequence? Sequence is a function, but it is denoted by a 1, 2, 3, etc. n by a finite sequence of n times. This is an understanding function f whose domain is the set of numbers 1, 2, 3, etc. Equilineous set. Two sets A and B are called similar or equinumerous if and only if there exists a 1, 1 function f whose domain is the set A, whose range is the set B. It is denoted by A similar to B or A difference B. Every set A is similar to itself. And note, if A similar to B, then B difference to A. It must be B difference to A. If A difference to B and A similar to B and B similar to C, then A is similar to C. Next, finite set. If the elements are finite, then the set is called finite set. A set S is called finite and the set to be containing n elements. If S is similar to 1, 2, 3, etc. n, the cardinal number of S is defined by the integer n is called the cardinal number of S. Next, note, if 1, 2, 3, etc. n, 1, 2, 3, etc. n, if n equal to m because of the similar set. The empty set is also a finite set. The cardinal number of empty set is defined as 0. Next, infinite set. Sets which are not finite are called infinite set. Example 2, 4, 6, 8, etc. Countably infinite. A set is said to be countably infinite if it is equinumerous with the set of all positive numbers. Equinumerous means the set containing what that the set satisfies the 1, 1 conditions and the range of set is B. Next, countable. A set S is called countable if it is either finite or countably infinite. Uncountable. A set which is not countable, then it is called uncountable. Next, according to the definition of countable set, we are going to see the theorem. Every subset of countable is countable. Let S be the given countable set and assume A is the subset of S. Then we are going to prove A is a countable set. If A is binary, then there is nothing to prove. If A is binary, then we can easily prove that A is countable. Suppose we can assume that A is infinite. That is, S is also infinite. If A is infinite, then the S is the superset. Therefore, S is also infinite. Let S equal to S and be an infinite sequence of distinct sums such that S equal to S1, S2, etc. Some dilemmas are going. Define a function and the positive integer as follows. Let k of 1 be the smallest positive integer that m belongs to A. That is our definition. K of 1 be the smallest positive integer. That integer must be belongs to the set A. Assume that k of 1, k of 2, etc. k of n minus n have been defined as like k of 1. Let kn be the smallest positive integer m greater than or equal to kn minus 1 such that sm belongs to A. Then we know that k is the order preserving because of it is the sequence of k1, k2, etc. kn minus 1. Therefore, m greater than 1 implies k of m greater than k. Then next we are going to form the composite function S composite k. The domain of S composite k is the set of positive integers and the range of S composite k is A. Therefore, S composite k is 1, 1. Next, the remaining two we have to prove k of n equal to k of m. That's all. Then we can easily prove that k of n equal to km and this n equal to m. Then finally we say that A is a countable set from the S is a countable set. Therefore, further S composite k is 1, 1. Then S of kn which is equal to S of km because of the composite function definition. Composite function definition said that if f composite g, then f of g of x. Thus, as like S of K of n, which is equal to S of Km, implies we can write that Skn equal to Skm. This implies that K of n equal to K of m. Thus, by the 1-1 function n equal to m, then we can prove that easily prove A is countable. Thank you.